split, we'll see that the eigenvalues are the zeros of the minimal polynomial. So, in other words, lambda is a zero of pt if and only if lambda is in the spectrum of t. Okay, so just to fix some notation, let's write down what the minimal polynomial of t looks like. So we'll take it to be a0 plus a1z plus a2z squared up to a m minus 1 z to the m minus 1 plus zm with no coefficient, well, with coefficient of 1 because it's monic, right? Okay, so then if we look at, let's back up here. This is an if and only if. So let's go in the forward direction. So for the forward direction, we're going to assume that pt of lambda is equal to 0. So suppose lambda is a root of the minimal polynomial. All right. Then we know that we can factor ptz as z minus lambda qz. And then just by looking at the shape of this product, you can see that q has to be monic. Because when we FOIL that back out, z times qz has to give us a zn term with coefficient of 1. So the coefficient of the highest degree term in q cannot come with a coefficient other than 1, or you'd end up with a contradiction. Okay, so now we've got that pt of t is equal to 0 on the one hand, and on the other hand, substituting it into the polynomial, we have t minus lambda I times qt. All right. Now, so this is saying that the product of this operator and this operator gives you the 0 operator, right? But it can't be the case that qt is the 0 operator. Because that would contradict minimality. Okay, so if it's not the 0 operator, then we can find some vector v with qt non-zero. And I guess I don't have to specify that it's not the 0 vector, because that would be, oops, I forgot to write the vector. The vector goes here. There we go. If v were 0, then qt would definitely be 0, so that's kind of obvious. Okay, so there's just a vector such that qtv is non-zero. Okay, but if I were to put that vector here, it would have to equal 0. So that tells me it has to be a 0 of this portion of the product. So that says then that that one's equal to 0. Which tells us that lambda has to be an eigenvalue. Okay. For the reverse implication, let's suppose that we've got an eigenvalue. So that means we've got a eigenvector v, so a non-zero solution of this equation. All right, so now what I'm going to do is I'm going to apply pt of t to this vector. But first, let's just note that if I apply t to v repeatedly, then I get lambda j multiplied repeatedly against v. So if I do pt of t applied to v, Well, I know that pt of t is the zero vector, zero operator, so this has to be equal to 0. Meanwhile, at the same time, this is a naught I plus a1 t plus all the way up to m minus 1 t to the m minus 1 plus t to the m applied to v, which is going to be by this equation right here, is the same thing as a naught plus a1 lambda plus a m minus 1 lambda to the m minus 1 lambda to the m multiplied against v, which is pt lambda times v. And then since v is non-zero, it must be the case that pt of lambda is equal to 0. So lambda is a 0 of pt, and that completes the proof in the backward direction.